specifically for interviews.
1, 2, 3, 4, 5.
They're just book smart.
Book smart people wouldn't do that. Book smart. That was more my point. Book smart people wouldn't be making out. We gotta hit the books.
Okay, so hello everybody. Sorry, we have to stop talking. We have to stop talking about sex now and get on with why we are here. Okay, so how's everybody? I'm still trying to get these things straight. When is the homework due?
Today.
Oh, that's awful. That means this weekend I have to write a new homework assignment. Yeah. So I will keep you in mind. So life is tough. I'm heading to San Diego tomorrow morning, but I will bring my work with me. So the IEEE. See, I am an engineer, despite what you might think. IEEE Photonics Society is having its annual meeting in San Diego, and so I have to go to it because I'm an engineer. But I will be back on Friday. Class next week will be, the engineers here are snickering. I can tell, that always happens. Engineers are snickering. So I'll be back on Friday. Lecture next week, just as usual. So last lecture we talked about the quantum mechanical theory of the nonlinear susceptibility, and we poured a lot into that lecture. Are there any quick questions before we move on? We have discussion later, as usual. Okay, so clearly there is more to be said about the nonlinear susceptibility that we calculated last time. And if there's time today, I'll backtread a little bit to treat some of the things that were left out of the last lecture. But the primary thing I want to do today is to forge ahead and work on the density matrix formalism of quantum mechanics, which will be very important, in its own right, and will be especially important when we get to talk about resonant optical nonlinearities a little bit later in the course. So let's just start in. So, and again, first from a fundamental point of view, we'll do the density matrix formalism of quantum mechanics, and then we will apply it to nonlinear optics. And again, why do we want to introduce a still more complicated formalism of quantum mechanics? It's because we can treat what are called mixed states. And I think I defined those, or at least conceptually defined those earlier. And the more formal definition will be developed as the lecture goes on. And from a formal point of view, it's that we can treat collisions, etc. Okay, so so let's formulate the density matrix. Let's formulate how this works. The first half a dozen steps will look identical to what we did in the last lecture, but then we will veer off into a different direction. But so that this is logically complete, I'm going to start at the very beginning. But no fear, we're going to veer off in a different direction very soon. So if a system, like an atom, is in a state that I'll call S. I guess it's better to be precise. If it's in a pure state S, it is described by the wave function psi S of R and T, and this wave function has to obey the Schrodinger equation. And I'll move up to here now. The Schrodinger equation, IH bar partial psi S with respect to T, let's put in the functional dependence, is equal to the Hamiltonian operating on psi S of R and T. And now the Hamiltonian we will represent as a, well, we'll decompose into the Hamiltonian of the free atom plus the interaction term. So H naught is the Hamiltonian of the free atom, and V of T is the interaction with the laser field in the present context. And we have energy eigenstates and the energy eigenstates are the form psi of R and T equals U of R let's use N as an index for these states. Un of R e to the minus E n T over H bar, where H naught on Un of R is equal to E n of U n of R, where, since we just went through this, I'm going to I'm going to leave out some of the words, where Um of R, Un of R, D3R is equal to delta Mn. Okay, so with only a slight exaggeration, this is a summary of last week's lecture. If there are comments, please ask. Let's make sure you feel comfortable about this, because if you don't, things are going to get tough in a minute. And then we argue that the energy eigenstates form a complete set. And thus, this state, psi S, that we started with here, can be written as a summation over all of the energy eigenstates N of C N S of T U N of R. Some purists typographical purists say that you should put this in parentheses so that people don't think that you're raising c to the power n. Okay, so let me just say it once in words so that we don't have to keep writing that in parentheses. Okay. So s is a superscript. It is not an exponent, which I think you would have thought anyway, but it's always worth to say these things. And again, this is a probability amplitude. It's the probability amplitude that this state, psi s, has energy E sub n. So let me just point out that quantum mechanics allows the existence of states that do not have a well-defined value of the energy, which at times in my life, especially when I was a beginning graduate student, worried me a little bit because I believed in energy conservation. But well, I think we have to live with it. That quantum mechanics, well, energy is conserved if you know the energy. If you don't know the energy, then energy is still conserved. It's just that you don't know what the energy is. But within the range of energy values that were in the initial state, that will certainly be the range of energies that are available as the state evolves in time. By the way, if the blue light starts flashing, let me know, because it means the battery's gone out. Okay, so this decomposition here says that if I want to know the time evolution of this state psi sub s, I have two options. Well, I have at least two options. One is to say this is a differential equation. I will solve this differential equation. And if you have a good computer, you tell the computer to solve this differential equation, and maybe it will give you the answer. I heard some of you complaining about Mathematica, and we know that you can always ask a computer program to solve an equation, but sometimes it will not. It will not give you, it just has trouble solving a partial differential equation. So a second avenue that's available to us is to note that if we know the time evolution of each of these expansion coefficients, then we can then we just use this equation to determine the time evolution of the wave function itself. And very often this is a more convenient way of proceeding, is to ask how do these evolve in time. Okay, so how do the C and ST evolve in time? Okay, so let's argue that this has to obey Schrodinger's equation, and then let's see what that has to say about these coefficients Cn. So just taking this, introduce it into the Schrodinger equation, we find that IH bar sum over n d Cn s of t dt un of r is equal to the sum over n of C n s of t h times u n of r. Now we play the same trick that we did last week. We multiply from the left by by u m star of r, and integrate. overall space. And you can almost do it in your head, right? You find that IH bar d by dt of CMS of t is equal to the sum over n of H, M, N, C, and S of t. And we can well, I guess I should define this. So we've defined some new quantities, H, M, N, and this is it's integral of U, M star of R, H, U, N of R, D3R. So this equation here we can consider to be the matrix form of the Schrodinger equation, and HMN are the matrix elements of the Hamiltonian. And oftentimes computers like matrices better than differential equations. So, written in this form here, it is often a form that's just easier to implement in terms of numerical analysis. Okay, any questions? Okay, so now we note that this is all for pure states so far. So in a sense, we have not introduced the key reason for the density matrix at all. But we are taking our quantum mechanics, taking the Schrodinger equation, and putting it in a form, well, that looks like a matrix. So, I mean, you can't have a density matrix if you don't have a matrix. So we're working our way up toward the goal that we have in mind. Let's leave that. Let me leave the last panel. Let me take a quick look at the camera. This is the first time I've done this without a video technician in the back of the room. So let's see what's going on here. It's still charging. If someone back here sees this start flashing, please let me know about that too. So I think we are. By the way, these files are multi-gigabytes long, so then I have to compress them and then I have to stitch them together. So I've learned much more about video technology than I ever wanted to know in taking on this task. Okay, so we know how the expansion coefficients evolve in time, but now let's talk about observables and expectation values. Another postulate of quantum mechanics is that any observable quantity, I'll just call it A for now. This could be position, momentum, energy, angular momentum, anything that you could go to the laboratory and measure. Any observable quantity A is associated with a Hermitian operator, may as well call it A, but it's an operator and it has a hat on top of it, but it has to be Hermitian. And I guess for the mathematically inclined, why don't you tell me why it has to be Hermitian?
Because it generates view from.
Because?
It generates the view observable.
Right, well, yeah, yes. But the eigenvalues are real. I guess that's the mathematical statement, is that if you have a Hermitian operator, the eigenvalues of that operator will be real. Or, I mean, that's correct. Or if you express this operator as a matrix, then the eigenvalues of that matrix will be real. And observable, you'd better have real numbers if you wanted to correspond to an observable quantity. Okay, so according to quantum mechanics, in general, the expectation value of an observable quantity is obtained by taking psi s, complex conjugate, the operator A, and the quantity itself integrated over R, or in Dirac's notation, psi s, A, psi s. Now, let's write this in terms of the quantities C, M, S of T. So we just take our expression, which I guess I did erase. We take the expansion of the wave function in terms of the expansion coefficients, take that equation, put it here, and what you find is that the expectation value of A is equal to the sum over M and M of C, M, S star of T, C, N, S of T times A, M, N, where AMN is equal to U M star of R operator A U N of R D3R, which if you want can be written as psi M A psi N. Okay, so I guess, so what have we accomplished up to this point here? From a fundamental point of view, absolutely nothing. And, everything here rests on the validity of Schrodinger's equation, and it's simply a matter of choice whether you want to work with the wave function itself or whether you want to work with these expansion coefficients C. But I think this shows that once you know the expansion coefficient C, you can determine anything you might want to know about the quantum mechanical system. Now, key point. But what if the state of the system is not known? I mean, that is when the Schrodinger, that's when the wave function formalism breaks down. Because if the state of the system is not known, then how do you write down the wave function for that state? So we define the density matrix. I think Wigner is one of the people who's credited with introducing the density matrix formalism. Okay, so it's a definition. So rho n m. Let's define it to be a summation of all the possible states of the system times the probability that the system really is in state S times C m S star C n S. So I heard some of you fighting about who got to sit in the back of the classroom. That reminds me of a joke. You knew where this was heading. A bus driver who rarely went to church goes to church one Sunday and sits in the very front row, right looking at the minister almost in the face. And after the service, as he's leaving, shaking hands, the minister said, "This is the first time you've come to church, and why did you sit in the front row?" He said, "Because I'm a bus driver by profession, and I wanted to know what in the world you did to get people to sit in the back without having to yell at them." Isn't that cute? Okay, so this is a definition. And now this P of S is a classical probability. It's a classical probability. This is not quantum mechanics. It just means I don't know what the state of the system is. So I mean, the atom might be in its ground state. It might be in its excited state. There's a 30% chance that it's there and a 70% chance that it's there. No coherence, nothing like that. It's just that you don't know what the state of the system is. So this is the definition of the density matrix. There's a symbolic, I like to write this symbolically, although the symbolic definition will not be useful except for developing intuition. So let's just call this the intuition is that rho n m is equal to C m star C n bar. So it's the average over all the states. Or if you want to say, what type of average were you thinking of here? It's not a time average, it's an ensemble average. And what is the interpretation of the density matrix? Well, first of all, let's look at the diagonal terms. So rho n n is the probability that the system is in eigenstate M. I guess the way you see that is that if you have the same subscript here and here, well, that's just the squared modulus of C sub n. C sub n was the probability amplitude to be in state n, so the squared modulus of that amplitude is the probability to be in state n. More subtle is the off-diagonal. here, rho and m is the coherence between states m and m. Maybe I'll put coherence in quotation marks because, well, people call it coherence. So I mean, for lack of a better name, well, off-diagonal element of the density matrix maybe is a better name than the coherence, but its other name is coherence. And let me you can have an incoherent superposition, or you can have a coherent superposition. If you have an incoherent superposition, let's say that, as I said before, let's say that 70% of the atoms are here and 30% are here. Let's call this A and B. That means that the probability to be in level A is 70%. The probability to be in B is 30%, but that rho AB is equal to 0. There is no coherence between these states. When you say you have a coherent superposition, you mean that each atom, well here, 70% of the atoms were in this state, 30% in this state. When you say you have a coherent superposition, you mean that each atom is simultaneously 70% in this state and 30% in this state. And then you would say that rho B A is not 0. And maybe it's not easy to compare the two cases. Except here, rho BA is equal to 0. Here, rho BA is not equal to 0. So it's a more subtle concept. Are you with me? Or at least to lowest approximation. Thank you. Good. And then the very last issue here is, well, actually, we're back to observables. So let me keep that just for reference. So now, with this density matrix formalism, what is the expectation value of observables? So, well, let's just work it out. We want to know what is the for now, I'm going to use both angular brackets and a bar, and later on in the course we won't bother to do this. So what do I mean by this? The bar is the ensemble average. The angular bracket is the quantum mechanical average for the state S. Right. So we've had two types of averages in today's lecture. the average that we first said here. Then we introduced the density matrix, and then we said that we also have to do a classical average or an ensemble average. So let's just work this out. So this will be the sum over S of P of S of the expectation value if we are in state S. So this will be CMS star CNSAMN. And from now on, we will not belabor the obvious, and we'll just call this by this quantity here. It's a crucial conceptual point that there's two types of averages, but by convention, the world writes it this way. And you just are supposed to keep track of the fact that there's actually two types of averaging going on here. Now, we look at this equation, and you see that this is just the definition of the density matrix. So this can be written as the sum over n. Please note, okay, mistake. No, I just did it wrong. It's the I copied wrong. Okay, so the quantum expectation value of A is this quantity here. So I just forgot to put this symbol in place here. Okay, now you look at this and you say, well, this is nothing but, let me just interchange the order of summation. This is the sum of over n and m of rho n m a m n. And of course, there's a name for this. When you multiply two matrices together and then sum over both n and m, this is known as the trace, well, of rho times a. Like so. Okay, so this is another standard feature of the density matrix formalism of quantum mechanics, that the expectation value of observables is given by the trace of the density matrix times the matrix representation of that observable. Let's see if the windows will open. Nope, that wasn't the right thing to do. So we desperately need Robert, right? He was the only person. We each have our... Thank you. Isn't that something? They put this little door here for the sole purpose that you can reach in and open the window. Clever, right? Well, too clever for me, obviously. Okay, so this is our definition then. So this is a very, very brief. No, we're not done yet. So we've defined the density matrix. We've seen that the density matrix can be useful because using this equation here, you can find the expectation value of any observable quantity. But we still have one more thing to do. We need to know how the density matrix evolves in time if we want to know how these expectation values evolve in time. Okay, so next step. So next up, we need to know what is the time evolution of the density matrix. Well, since the density matrix is rho n m equals sum over S of P of S, C M S star C N S, just differentiate. D by dt of rho n m is equal to the sum over S of d by dt of P of S times C M S star C N S. That's the derivative of the first term. And now we want to take the derivative of this product here. The second term we can write as the summation over S of the P of S times C M S star d C N S dt plus the derivatives taken, plus the derivative taken on the other term, d C M S star dt CNS. Okay, now we have two very different types of time evolution. This is Hamiltonian time evolution. And we can determine this by the matrix form of Schrodinger's equation. And this first term here is the d by dt acts only on this. Let me just make it clear. Let me make it clear that the d by t acts only on this. The change, I'll even put knowledge of the quantum state. So these two contributions have a very different origin, and we will deal with them one at a time. And let's first deal with the Hamiltonian part, because that's the part we understand better. So first of all, the Hamiltonian evolution only. We would then have d by dt of rho n m is equal to the sum over S P of S times I over H bar. But now let's go back to the matrix form of Schrodinger's equation and substitute in, okay, go back to your notes, find out what d by dt of this is, and just put it here. Find out what d by dt of this is, put it there, and then I'm going to write down what you get. I think I put this in the wrong place. I H bar So now we have to sum over some new variable, let's call it new, C N S C new S star minus C M S star C new S. H new M minus C M S star C new S H N new. And let's put parentheses like so. Okay, so writing this down, I see it's not entirely obvious, but just do it. It's just a plug-in, and you get this. And now we can write this as d by dt of rho nm is equal to I over h bar. I'm going to pull this inside of the summation. This combination now with this together is just the density matrix itself. So I over h bar sum over nu of rho and nu h nu m minus h and nu rho nu m. So just by performing the just by introducing the new the form of the density matrix, and now you have something. You have something minus the same something taken in the opposite order, and we call that the commutator. So we can write this as d by dt of rho n m is equal to I h bar rho h minus h rho, or minus I h bar h rho n m. So this is, well, let me do it, or d by dt of rho n m is equal to this. So this is the equation of motion for the density matrix. How many of you have seen this before? Yeah, okay. Okay, so this is the density, this is the equation of motion of the density matrix. In subsequent calculations, we will take this as our starting point. Well, of course, except that we're not done. This is only the Hamiltonian evolution part. Let me write it here. Robert, we were just commenting, this is the first time I ever had to open the window on myself, by myself, and I failed. Okay, so now introduce relaxation phenomena. We will do it phenomenologically, which is how it's usually done. some people think that they are smart enough that they can actually calculate this. They say, oh, I understand collision theory, and when two atoms collide with one another, I will just write down the interaction Hamiltonian for that collision, and I will find how much the state changes as a result of propagation. But we will not do that. And in fact, it's except for the most advanced treatments, one does not need to do it that way. Most people proceed the way I will show you now. And in the book, I point out, well, because it's phenomenological, there's more than one way you can do it. So some people do it one way, some people do it the other way. I'll just give one method here for now. So this is the most common procedure. So we say that d by dt of rho nm is minus I over h bar h rho nm. So this is the Hamiltonian part. And then gamma nm times rho nm minus rho nm equilibrium. Now, it is so conventional that when you see an equation like this, you assume that you're supposed to sum over repeated indices, that I will point out that we are not summing over repeated indices here. So, gamma nm is the relaxation rate of rho nm. Rho nm equilibrium is the thermal equilibrium value of rho nm. So this equation here says that any element of the density matrix will relax or decay to its equilibrium value at a rate given by gamma nm, or equivalently in a characteristic time equal to the inverse of gamma nm. Now, there are some physical assumptions that are often made in conjunction with this, and one of them is that rho nm equilibrium is equal to 0 for n not equal to m. Okay, so the thermal equilibrium value of rho nm is equal to 0. Could anyone suggest a reason why this is a physically realistic assumption under almost all circumstances?
Isotropic.
That's not what I had in mind. I'm going to get a drink of water, and that will give you exactly 70 seconds to think of the answer. Okay, any thoughts? You know enough.
If it's a coherent superposition for off-diagonal elements, it'd be really surprising for things to stay in a coherent superposition for all times t.
Yeah, okay, yeah, that's it. Everybody heard? Agree? Now that you hear it, it's obvious? Okay, now, let me say it in my own words, which is exactly the same thought. Here's an atom with levels A and B, and we are in thermal equilibrium. If the temperature is high enough, you could imagine that some population will be up here. How much? I'm testing you on your undergraduate statistical physics.
E to the minus of the energy difference over K.
Okay, let's call this EBA. So E to the minus
BEBA
E
over K.
BAA over KT. And this is the fractional population in level B. And what is this called? It's the Boltzmann factor, I guess. Okay, yeah. And if you have population in many, many levels, you have to divide this by the partition function. But let's assume that the population in level B is very small, and then it's just exactly what he said. Your name?
Chris.
Chris. Exactly what Chris said. Okay, so you can imagine there's going to be population there. But in my wildest dreams, I cannot imagine that atoms are going to bounce into one another in such a way as to create a coherent superposition of levels B and A. By the way, I put A here and B here. Believe it or not, in Arizona, they put A on the top and B on the bottom. That is why you came to Rochester, right? Now, that's what Marlin Scully does in all of his books. And he was at Tucson when he wrote his first lasers book. So, I mean, most of the people in Tucson still do it the other way around. Okay, I love to laugh, but if you're doing laser physics, this is the initial state, and that's the final state. So it's not quite as stupid as it sounds. But it's still pretty. To me, it's still pretty stupid. Okay, so the physical assumption is that the thermal equilibrium value vanishes for the off-diagonal elements, and often that rho n equilibrium is equal to 0 for n other than the ground state. Now, if we were doing microwave photonics, no, it's just that this is usually very small for optical transitions. This is another one that you're supposed to commit to memory. What is KT for at room temperature?
It's like 1/40 electron volts. Or
Yep. Okay, and most transitions in the optical are a couple of electron volts, so this is a very, very small number in the optical at reasonable temperatures. Even at unreasonable temperatures. I mean, you really have to work very hard to get appreciable population thermally excited into the excited states. Okay, I guess now the question is, I said phenomenological, but still, how would we go about estimating the value of gamma NM? Well, you can show the following. In fact, not only can we show it, but I'll actually sketch out how you show this. That gamma NM is equal to 1/2 of gamma N plus gamma M plus gamma NM collision. And here, gamma N is the radiative decay rate. Level M, well, and of course for level M the same, and gamma NM collision is the collisional, well, this is the collisional, it's the collisional dephasing rate. And this is approximately equal to the collision rate. So using what you learned in kinetic theory as undergraduates, you can estimate the rate at which atoms in a vapor will undergo collisions. And that's the quantity that goes here. So I find this a very nice equation. I mean, some were ugly, the ones that go on over 3 pages, but there's a lot of physics here. There's 2 ways at which you can lose coherence between levels N and level M. You can lose population. I mean, if there's no population in the level, there's certainly not going to be any coherence. So you can lose coherence in the obvious way by having population decay out of the levels, or collisions can affect the decay rate in their own way. Now, I guess following through on this, why is there a factor of 1/2? Following through on this, why is there a factor of 1/2? Next week, Friday, we will have a class competition. I'll write this down so I don't remember. so I don't forget to charge you to do this. I'll give you a hint. The answer's in the book. This is not going to be a horribly difficult intellectual endeavor on your part. But so I tried to argue that this equation makes sense. Even the 1/2 makes sense. So, so why is there 1/2 in gamma n m? I guess now that I've told you the answers in the book, this would not be a good homework assignment, would it? So this will be just for fun, for your personal edification. We will come back to this next week in class. Okay, so we have our. Okay, so this is the equation of motion that we will use for the density matrix. Let's erase everything else and put a box around it, like they do in high school textbooks, right? You've noticed that, right? In college, we think we're too sophisticated to put boxes around the important equations. This is actually to remind me not to erase it. Okay, now, so now let's apply this to optical physics. And that means that V of t is mu time, I'll write it in the scalar form. Okay, so in the electric dipole approximation, the interaction energy is the electric field strength of the incident laser beam times the dipole moment operator of the atom. Now, well, if you couldn't solve Schrödinger's equation analytically, it perhaps comes as no surprise that you cannot solve the density matrix equations exactly. So we have to use perturbation theory. Okay, so let's be more. Let me be more formal about this. Let me polish this a little bit. So we're going to take the Hamiltonian to be the atomic Hamiltonian plus the interaction Hamiltonian that I have already written here. We know we're going to need the matrix elements of the Hamiltonian to apply this formalism. So first of all, what are the NM matrix elements of the atomic Hamiltonian? Or I can write this as N H naught M. And this is E N delta N M, making use of the obvious statement that the Hamiltonian is diagonal in the basis of its own eigenvalues. We defined the eigenvalue, we defined our basis set to be, if it gets cold, please go ahead and close. We defined our basis set to be the eigenstates of the Hamiltonian. So then, of course, the Hamiltonian, when represented in terms of its own eigenstates, will be a diagonal matrix. But that is not the case for V I'll drop the T now just for convention, just for ease of representation. And this is, there's no obvious simplification. So we will just leave it in this form for the present. So we are told that we have to evaluate this commutator. Now, in some ways, you don't have to evaluate the commutator. You can just look back about 12 equations in your notes to see where this came from, and you can just write that down. But let's say that terrible misfortune and you lost your lecture notes and you lost your copy of my book. So and all you know is this. So we have to expand this commutator to find out what the more explicit form is of the equation of motion. So, let's see how to do that. So we are asked to determine what the NM matrix element is of this. So you say, well, what is this? This is H rho NM minus rho H NM. And now you can always introduce the identity operator anywhere you want because that doesn't change anything. And we will write the identity operator as the sum over nu of nu. Again, making use of the assumption that the eigenstates form a complete basis. Then the identity operator can be written in this form here. And we do the same decomposition here. We introduce the identity operator here. And we then find that H rho NM, I'll pull the sum over nu out front. We have H nu rho NM minus rho nu H and M. And now let's explicitly work out what the NM matrix element is going to be. So this is the sum over nu of N H nu rho M minus N rho nu H M N square bracket. And now whenever we have an H, let's replace it by H naught plus V. And here we replace this by H naught plus V. I guess there's actually room up here. So we find that the commutator of H with rho is H naught N rho N M minus rho N M H naught M M. So that is the Hamiltonian part. That's the free atom part, rather. But we also have the sum over nu of V and nu rho nu M minus rho and nu V nu M. Okay, so this is the commutator that needs to be introduced here in order to calculate the time evolution of the density matrix. Okay, so let's do that. Let's assume that we take this, we introduce it here, and let's see, this term is what it is, but this term now expands out to this combination here. So let me here then write down what the equation turns into. So we find that d by dt of rho and m is equal to minus I omega n m rho n m minus I over h bar, sum over nu v and nu rho nu m minus rho n nu v nu m minus gamma n m rho n m minus rho n m equilibrium. Oh, and so I've introduced the definition of omega n m, which is what you would have guessed, I hope. Or at least this is very, very conventional in optical physics, that omega n m is the energy difference between level n and m, written in this order, divided by h bar. And alternatively, sometimes we will write this as d by dt of rho n m is equal to minus I omega n m rho n m minus I over h bar v rho n m minus gamma n m rho n m minus rho n m equilibrium. The point being that you say, why do we do it at all? Well, because the free atom part of the commutator takes on this wonderfully simple form. This commutator does not take on a particularly simple form, so sometimes notationally we want to leave the interaction part written this way because it's a bit more compact, but this is no more or less compact than what we started with, but actually shows the physics very nicely. Okay, any comments? 10 o'clock. So I guess it's time for a short break. It's 12 o'clock, exactly 1.5 hours. So we will continue this, take 5 minutes or so. No need to take much more than 5 minutes. I will pause the camera. Okay, so let me now erase everything except this, because this is the form that we'll be using now. So now this one goes into a box. It's getting a little chilly. Okay, so we want to solve this. So let's call this the perturbation theory solution. Okay, we've gone through the formalism of adding a lambda, equating equal powers of lambda on both sides of the equation. We've done it twice already. This time, let me just write down the answer. Once you've gone through that a few times, you can almost by inspection see where it's going to end. And it decreases the number of intermediate steps dramatically. So we want to seek a solution of the form rho n m is equal to rho n m 0 plus rho n m1 plus rho n m2 plus dot dot dot, and the number here is the order of V. That is, here you have terms that are proportional to V squared. Here you have terms that are linear in V. Here you have terms that are independent of V. So carrying through on this perturbation expansion, you find that rho n m0 dot for time derivative is equal to minus I omega n m rho n m0 minus gamma n m rho n m0 minus rho n m equilibrium. Rho n m dot first order correction is minus I omega n m minus I omega n m plus gamma n m rho n m 1 minus I over h bar V rho 0 n m. And just so that you see the pattern, let me go one order more. Rho n m2 dot is equal to minus I omega n m plus gamma nm rho nm1 minus I over h bar, sorry, 2, I over h bar, v rho 1 and m, and the same thing up to higher orders. So now that I've written it down, it's easy to see by inspection that this is correct. Everything here is of 0th order. This is a first order. This is a first order. Rho is to 0th order, but V is to first order. Everything here should be second order, first order times first order is second order. Okay, so now we solve in sequence. Okay, so the first one is not really a solve. It's stating your initial conditions. So rho 0 n m is equal to rho n m equilibrium, where rho n equilibrium is equal to 0 for n not equal to m. Let's make only this assumption for right now. Now the second equation is a first order equation with a prescribed inhomogeneous part. So we need to evaluate this commutator and then perform the integration. Well, let me write down formally what this is. So rho 1 n m of t is equal to the integral from minus infinity to t minus I over h bar, commutator of v, well, let's just put the time dependence so that I can point out that this is t prime of v of t prime rho 0 and m e to the I omega n m plus gamma n m times t prime minus t dt prime. I guess formally you write down the green function for this, although personally I guess the answer, and then differentiate this and make sure that it does indeed satisfy this equation. Etc. So I mean, all of the higher order terms, all the higher order equations are of the same functional form. So to find the equation for rho 1, you just for row 2, you just take each subscript and you add 1 to it. So the equation for row 2 would have a rho 1 here, and that's it. Yes?
So, looking at just row 1 and then we had an I omega nm plus like all real gamma. So why
There's something wrong. Okay. Thank you. Thank you. Thank you. I put the parenthesis in the wrong place. Then you say, why is it a plus? Well, because the minus sign is with the t. Okay, so this this is the formal solution to the density matrix equations of motion, and For the reason we just gave. Okay, you see that before we had to ignore the contribution from minus infinity for no particularly good reason. But looking ahead, you can see that there's damping here that goes with time. So any initial condition will have decayed away at the present moment of time. So yeah, we've worked hard to handle that point, but I guess there's some elegance in the fact that we do not have a formal divergence in our theory. Of course, if we were high-energy theorists, divergences wouldn't bother us, right? Oh, we just ignore that. Okay, so let's take this then. This is the first order correction to the density matrix. This will allow us to calculate the linear susceptibility. So let's do that. So calculate the linear susceptibility. Let's see. Let's make sure I didn't change notation here. Oh, I did not change notation, but note that t prime is the dummy variable, so that the part that depends on t we can take outside of the integral. So I will take this equation and write it in still one different form before we start evaluating. So rho n m 1 of t is equal to e to the minus I omega n m plus gamma n m t integral minus infinity to t dt prime minus I over h bar commutator of v of t prime with rho 0 e to the I omega n m plus gamma n m t prime. Well, since we're actually going to be plugging in, I guess, v of t prime is minus mu times e of t prime. And let's take e of t prime to be the summation over p of e of omega p e to the minus I omega p times t. And I guess p, the summation goes over both positive and negative frequencies the way we've written it here. So let's now evaluate this commutator, which says that v of v of t prime commutator with rho 0 is the sum over nu of v of t prime and nu rho nu m of 0 minus rho n nu of 0, v of t prime nu m component. Now for v, let's introduce mu times e. And we find that this is equal to minus the sum over nu. Yeah, minus sign from here. Minus the sum over nu of mu n nu rho nu m 0 minus rho n nu 0 mu nu m times e of t. And now this simplifies just a little bit more. And I'll put it over here. Simplifies just a little bit more. So we can write this as minus rho 0 m minus rho 0 n times mu n m times e of t. Okay, so the commutator of v with rho 0, and of course rho 0 we assumed had only diagonal elements. So the commutator, well, depends only on the diagonal elements, because the 0th order, that's all you have. And this takes a fairly simple form. It's the difference in the population of two levels times the interaction energy mu times e. So just store that away, because when we get a couple steps further, you'll see how this actually shows up in the final formalism. Okay, so we needed to know what this commutator was. We now know what the commutator is. We take this and introduce it here. Well, I guess just so we have these steps complete, let's remember that E, this was T prime, of course, right? That E of T prime is the sum over P of E of omega P e to the minus I omega P times T. Okay, so that's what goes into, well, actually, I did have it here. You can't see the board if you're standing too close to it. Okay, so we now want to put this and this into here and perform the integral. So we perform integral, and we find that rho 1 n m of t is 1 over h bar, rho 0 m minus rho 0 n times the sum over all frequencies that are present times mu n m e of omega p e to the minus I omega p times t. And then from integrating over this exponent that pulls the coefficient of t down into the numerator. So we get omega n m minus omega p minus I gamma n m. So the density matrix depends on the population difference between the two levels, and something that looks very similar to what we had from the perturbation theory of the wave function. Now, we can relax. Now the calculation proceeds just as it did for the wave function treatment, except that, well, in one step, it'll proceed just as it did before. So what do we want to do? We want to calculate the expectation value of the dipole moment at time t, and we know that this is the trace of rho 1 times the operator for mu, and that this is equal to the sum over n and m of rho 1 and m mu mn. So we have this, this is what it is. It's the matrix element of mu. So we put this together, we perform the trace, and we find that this is the sum over n and m of 1 over h bar rho 0 m m minus rho 0 n n times sum over p of mu m n times mu n m e of omega p e to the minus I omega p times t omega n m minus omega p minus I gamma n m. Okay, so we now have an expression for the dipole moment, the expectation value of the dipole moment introduced into each atom. We find an interesting fact that we could have guessed. If level M and N have equal populations, they will make no contribution to the dipole moment associated with the transition from level M to level N. You could have guessed it, right? Well, you could have guessed it once you know the answer. And at the risk of giving a false analogy, if the level populations are equal, the absorption rate and the stimulated emission rates will be equal, so there will be no dipole moment connecting the two. Because the dipole moment connecting the two is what would drive a transition between the two levels. Okay, so now there's some bookkeeping involved to turn this into a susceptibility. Let's not go through the bookkeeping. We did this last Friday. You know, you say, now I will multiply by the number of atoms per unit volume. I will decompose this into its Fourier components. I will determine the polarization vector P that occurs in Maxwell's equations. I will define the susceptibility as the coefficient relating the polarization to the applied electric field. I mean, these are definitions that have gone back almost to the first lecture. So we just implement, we implement the definition of the susceptibility. And here's what we find. Now, all through this lecture, I have been simplifying things. If I had treated these as vectors from the very beginning, we would have found exactly the same equation, but with the dot product between the dipole moment, matrix element, and the electric field amplitude. So at this point, let me put it in. I did not want to have horribly complicated equations on the board. So at this point, I'm going to go back to this. I think in the book, it is given with, it's given in vector notation from the very beginning. So we find that chi1 ij at frequency omega p is n over h bar, sum over n and m of rho 0 m minus rho 0 n times mu I m n mu j n m omega n m minus omega p minus I gamma n m. There are two ways of writing this result. They are both very, very useful, and they display complementary intuition. This form here tells you that there will be no susceptibility associated with the N-M transition if the two populations are equal, something that we pointed out here. But there's no reason why I cannot turn this into two separate summations. Why I cannot turn this into two separate summations, 1 over m and 1 over n. Then, since n and m are dummy indices, I will replace m with n in one of the summations, but not the other. Okay. A trick that we've also played earlier this semester. And then we can write this in the form n over h bar, sum over n and m, rho 0 m times mu I m n mu j n m over omega n m minus omega p minus I gamma n m plus, and the second term is mu I n m mu j m n omega n m plus omega p plus I gamma n m. So now we are back in a form in which one of the terms looks like the resonant term and the other looks like the anti-resonant term. Or vice versa. Because since n and m are still dummy indices, who's to say that omega nm is a positive quantity? If omega nm is a negative quantity, then this is the resonant term and this is the anti-resonant term. So you can amuse yourself by looking at this equation in its various limiting forms. I will do it for just one limiting form here, and that is the one in which all of the population is in one level. I'll call A, and maybe there are many other levels up there. Which I will call N. And we then find that chi1 ij and omega p is equal to n over h bar times mu I a n mu j n a over omega n a minus omega p minus I gamma n a plus mu I n a mu j a n omega n a plus omega p plus I gamma N A. So I think this is identical to the form we derived last week. So I guess as a matter of personal taste, how much we've accomplished. Last week we introduced this I gamma in an artificial manner to keep this from diverging. This week we derived it, well, but we introduced the I gamma artificially in an earlier part of the calculation. Right? I said we will introduce damping phenomenologically, but still, this seems to be a more robust way of treating the problem of the linear susceptibility. Even though we just did it last Friday, we can call this a review. I'm just going to, let's take a look at this equation and make sure we all understand it. Let's consider the A going to N transition. So the lower level is here's a particular upper level N, and we apply a laser at frequency omega p. Now let's consider omega p approximately equal to omega NA. We can then ignore the anti-resonant term. And the way this is written, I mean the second term. And then if we plot this, we find that the imaginary part is a Lorentzian centered on omega NA, and that the real part looks like this. So this is the imaginary part of chi1, and this is the real part of chi1. And of course, n is the square root of 1 plus chi1. So if you want to know how does the real and the imaginary part of the refractive index depend on the susceptibility, you have to calculate a complex square root. But still, roughly speaking, the imaginary part of chi is what describes absorption, and the real part of chi is the refractive index, or the variation of the real part of the refractive index. And I'm going to write myself a note. That sounds interesting, doesn't it? To do the complex square root and see if our intuition becomes any different. Okay, any comments? I'm going to get another small drink of water, and I will be right back. I keep forgetting to bring water to class with me. Okay, so let's just talk a little bit now. You know what comes next, right? Say, well, if you do it for chi1, you can do it for chi2. If you do it for chi2, you can do it for chi3. Let's just, but we did that last week. I mean, for the wave function treatment. I will encourage you to read in the book the section on the density matrix treatment of chi2 and chi3. You will find some interesting features there. One is that you can derive these expressions for chi2 and chi3. Remarkably, you will find that you get a different number of terms than you did before, which is a little bit strange. I mean, it just comes out that way. But in certain limiting cases, you can combine them in such a way that you get the same result as before. And in particular, if you ignore all the I gammas, so in both formalisms, in the wave function formalism, there never should have been an I gamma, so drop it. In the density matrix formalism, you say I will work only very far detuned from resonance, and then the I gammas don't matter. Then you have two expressions that look different, but if you can sum them up in just the right way to show that they're equivalent. If that's your idea of fun, I encourage you to do so. At one point in my life, I thought that was fun, and some of the details you will find worked out in the book. The basic intuition, I would claim, is no different from what it was last week. The resonance structure of the nonlinear susceptibility is very, very much the same. So let me ask if there are any questions about today's lecture. So I guess we have another 45 minutes, and so let's open this up for discussion. And if you don't have enough, and if the discussion does not take the entire remainder of the lecture, then I will, I hope I have it with me, I will back up and, I will back up and do a few pages of my lecture notes that were omitted from last Friday. Okay, so discussion time.
For the gamma treatment, I mean, for those systems that do not approach to equilibrium, eventually, so do we still allow to use to write down, to use the relaxation approach? Because in your treatment, it means that the system will eventually, you assume, it will go approach to equilibrium. But I mean, for those turbulent state, I mean, for some very long need, they will, for some situations such that the system will never go to equilibrium, and then the thing we learned today may not be applied.
I think I chose my words poorly earlier on. If you turn off the laser field, the system will relax to its equilibrium state in a time of gamma, rate of gamma nm. When the laser is turned on, that's different. The relaxation is still there. The transients will die off. So let's say you turn on the laser field. The atomic system will have, say you abruptly turn it off, turn on your laser field. There will be a steady state response to the atoms, and there will be a transient response. The transient will die out. The sinusoidal steady state solution, for the linear case, let's talk linear. The sinusoidal steady state solution will become established within a time equal to 1 over gamma nm. So I forgot to say that. Well, I forgot to say it. But I said that we have a quasi-homework problem for next week that you're going to see where the 1/2 comes from. And in deriving the 1/2, you will see that you want to determine the time evolution of the system in the absence of the laser field. So does that clarify the situation? Okay, good. Thank you. Is there more discussion?
I guess just like administrative question. So if we were interested in the solutions to some of these Mathematica assignments,
Yes.
where will they be posted? Or called out?
No, we will provide. I thought they were actually. No, so I need to find out about that. I know that both the so Mohammed is the head TA, but he runs them by Zahir in Ottawa. Because Mohammed's being paid to do it. so Mohammed writes the solutions, then he sends them to Mohammed, and then he sends them to Zahir and says, do you think these solutions are correct? Zahir says yes. That happened several days ago. I think they're posted. I think Mohammed forgot to tell you where they are posted. So if I...
To our assignments.
Yeah, same thing. Where are grades? How did the student get grades? And where are solutions posted? Okay, so thank you for bringing those issues to my attention. Mohammed is very conscientious, but like all of us, he sometimes needs reminders. He needs fewer reminders than I do. But I'll find out what happened to your solutions. I know they're done. So I'm just taking, I'm doing my own stuff. I'm doing my own thinking here. So I want you to interrupt me, but, so I mean, I'm doing sinister things. I'm trying to find very, very exciting homework problems for you to do. So it pays you to interrupt my train of thought. Yeah, good. No, I'm really thinking it's a nice homework proposition.
At what point does our primitive solution fail because our dipole approximation fails?
Yeah, okay. So, I mean, there's more than one way that the perturbation solution could fail. The obvious one being that maybe the series does not converge. My theorist friends say, oh, that's not a problem. One should distinguish between asymptotic convergence and convergence. I say, I've forgotten. It's a long time since I was a graduate student. Well, what does that mean? I say, well, it's asymptotic. It means it doesn't converge. So why would you want a series that doesn't converge? They say, you don't get it, do you? You're not a mathematician. I said, yeah, I guess I'm not a mathematician. Okay, so maybe this series does not converge. So that would be the obvious thing to worry about. And in which case it means that you did the wrong approximation. You need to do a different approximation. And I think we will find one in the chapter on the resonance nonlinearities. I believe that the perturbation solution will not converge there, so we just find a different way of handling the problem. Now, you also ask about the dipole approximation. And you said the dipole approximation breaking down. I wouldn't use the word breaking down. I would say that perhaps other multipoles become important. The selection rules are such that the higher order multipoles can couple atomic states that are not coupled in the electric dipole approximation. So I mean, that's the main thing that happens, is that states that were not, states that would not produce an optical response, whether linear or nonlinear, in the electric dipole approximation do yield a response in the higher order multipoles. If the same transition can be excited either by an electric dipole or an electric octopole or whatever, almost certainly the electric dipole contribution will be much more important than the higher order solution, than the higher order multipole. And I have this strange recollection that optical activity depends on the magnetic response. Anybody have thoughts on that? None at all. Okay, so this goes on my list. Great homework problem. What optical phenomena depend on the magnetic dipole? And especially optical activity, etc. One of my former students really specializes in this, so I will write to him and I'll try to get an answer. Former students are great, by the way. They do your thinking for you. Okay, so good question. May show up in the homework, of course. It was that good. You should feel proud of yourself. Well, you're going to get homework. You would rather it be an interesting homework problem than a non-interesting homework problem.
I want it in class.
Oh.
That was the look.
Oh. Okay. Other discussion.
Actually, I wonder. I'm interested in the treatment in gamma. I mean, does that mean if we don't know something and then we always use the relaxation approach? For example, for some interaction between a system and then you don't know such a term and then you notice that the dimension is the inverse of time and then you always try to put some relaxation approximation to the system and then it may think a lot simpler, but does that make sense all the time?
Okay. Now that I know where the thought is heading, would you repeat yourself, please?
I mean,
Yeah, so just start over. I mean,
Yeah,
there were too many. I mean, there were too many issues that were wrapped up in that
yeah,
statement.
because in the treatment of gamma, we saw a term that we don't understand what is the exchange of knowledge for the derivative of PS, and then you say we don't know such a term, and then we try to we adopt the relaxation approach.
Yeah.
And then my question is, does that mean if we don't know something and then we, for example, in some system of equation and then we don't know something and then we can put the relaxation approach in to represent such a term, and then my question is that always true or is there any limitation for us to do so? When it fail?
When does our phenomenological treatment fail?
Fails, yes.
Okay, so I mean, there are. Okay, there is our phenomenological treatment, and then there are phenomenological treatments. But I can tell you where our approximation failed, because in the book, in a very, very boring and uninspiring section, I think it's for the two-level atom, I show that there are several different phenomenological relaxation models that you could adopt. So let me just give you one example here of what can go wrong. Okay, so model 1, this is the one we just dealt with today, and we said that the relaxation went like gamma nm times rho nm minus rho nm equilibrium. So let's say you have level N and level M, and we have said that each one relaxes independently. But now model 2, I won't write down the equation, but let's say this is n and this is m. Now, when this level, I'll put this O for other, when this level loses population, it could lose population to this level, or it could lose population to these other levels. I think we really get in trouble if most of the population that leaves level M ends up in level N. So this mathematical model does not conserve population. I mean, if you lose population here, it says, well, it goes into the reservoir. It goes into the reservoir is the language that people would use. But if you have a two-level atomic system, or maybe I should say if the two-level model is a good approximation for that system, the population leaving here will necessarily end up here. So that is outside of this model here. So when we get to the two-level atom, we will introduce a model that conserves population. This does not necessarily conserve population. This is the model that Bloomberg used in his early papers. So it's just a model. As we saw today, I mean, it's a fairly easy model to implement. If you start keeping track of the population in each level and asking where does it go when it decays out of one level, what level does it end up in, it's a bookkeeping nightmare. I mean, not conceptually difficult. I mean, not difficult at all, except a real nuisance to deal with. So, I think that gives you some idea of. Oh, and then there's the Markovian approximation, all these other things that. I mean, well, that was the thought question for next week. But if you assume a damping rate of this form, you will get exponential decay. But not all physical systems show exponential decay. If you're interacting with a reservoir in a complicated manner, perhaps the decay will not be exponential. And if there's a memory in the system, then the system is called non-Markovian. But you ask, how in the world could there be a memory in the system? So again, just an example, if this is level n, and if this is level n, and this is level m, but perhaps there are many fine structure or hyperfine structure magnetic sublevels associated with this. And now collisions can kick you from here into one of these, the atom stays there for a while, and then it gets kicked back and then decays. So in these more complicated relaxation schemes, you might have something other than just simple exponential decay. But I don't have anything deeper than that to say about that point. More discussion. If you're not careful, you'll have to hear me lecture.
No, I
Oh, yeah. I knew that would do it.
So actually, my comment about thing we learned recently is, I mean, even though we are talking about the nonlinear optics, but we are not solving nonlinear equation, but we are solving a linear equation. It is so different from a nonlinear fluid dynamics.
Yeah.
So I mean, it is just about the nonlinear response, but not but the whole equation of system are all linear. Am I right? So far up to this moment, it seems that it's very easy for us to derive,
Yeah.
to predict everything precisely.
No, I have to think carefully. Well, of course, you're right, but is that because of the nature of the approximations that we
Yes.
made? No, it's because I have to think. I have to think. Okay. I mean, it's a deep question. In what sense is this really nonlinear? Well, we know, well, but even if we don't know the answer, let's try to figure out the answer. So the nonlinearity comes in because P is a function of E. For example, P is equal to chi1 E plus chi2 E squared plus dot, dot, dot. I'll just show it symbolically that P is a function of E, and the wave equation is that the Laplacian of E minus n squared over c squared partial squared E with respect to t squared. If I've dropped a minus sign, we'll worry about that later. 1 over epsilon 0 c squared partial squared p of E with respect to t squared. Now, we have set up the problem in ways that we think we can solve it. But let me just write this mark. But I think in general, you have a wave equation with a inhomogeneous term that depends on the solution that's on the left-hand side. So, I mean, if you want to make this more difficult than it is already, I think that you can be accommodated. Just solve it this way. We have consistently broken things up into orders of nonlinearity, but then the comment was that maybe this Taylor expansion will break down, and if the Taylor expansion breaks down, then the whole idea of breaking this up into terms of this form breaks down, and then you have to deal with an equation of this sort here, where the source term depends on the field, which is governed by a wave equation of this form. So I think this one looks inherently nonlinear. Now, can we turn that into a homework problem? No, that one scares me. Question? Now, I have a very nice 10-minute lecture that really, I think, ties all of this together. I mean, this has been so formal that I want to tie this into, at least in concept, what might go on in the laboratory. This is Miles and Harris from the 1970s. And they were dealing with third harmonic generation in alkali vapors. So here's an example. You take light at frequency omega, and you're trying to turn this into light at frequency 3 omega. And let's say you have a vapor of sodium atoms, and you might ask, well, of course, if you care about the exact frequency, then that's not the right way to ask the question, and they address that question too. But if you say, I just want to create a lot of light in the UV by taking a visible laser and frequency tripling it, what is the best frequency to use? So So first of all, they calculate chi3. Yeah. No. I mean, I'll just call it chi3 of 3 omega, without saying 3 omega equals omega plus omega plus omega, because it's obvious. And they assume that the light is linearly polarized. Then we don't have to keep, then we don't have to explicitly treat the tensor nature of this. So it's called sum over A, B, and C, mu G C, mu C B, mu B A, mu A G, times 1 over omega C G minus 3 omega omega B G minus 2 omega omega A G minus omega plus plus plus. So this is the resonant term, and these are the 3 partially anti-resonant terms, which we talked about just last week. So now let's draw a picture of what this might look like. So here they're trying to do third harmonic generation. I'll draw dashed lines. This is G, this is A, this is B, this is C. But now, they point out that you might think that this is still a horrible mess to try to calculate this, but then they remind you that the ground state of sodium is an S state, meaning L equals 0. So when you sum over A, you only need to sum over the P states. Then when you sum over B, you sum over S and D states. And when you sum over C, you have to sum over, somebody tell me. blankety blank. Dipole selection rules. We will take. We will write down all proposed solutions and then take a class vote on them. Now, I'll give you 2 minutes to think. First, were people following me with this? Mu GA. This would be non-vanishing. If the ground state is an S state, it can couple only to a P state. If this is a P state, A has to be either an S state or a D state. But now, what about state C?
You need P again as well, right?
You need,
P.
exactly. But don't tell them why. Okay, now, so why is it that only P states can occur here? If you look at this, you'd say, gee, there's a lot of things that you could put there. But now look at this one here. C has to couple back to the ground state. The ground state is an S state, so this has to be a P state. I assume that was your logic?
I was just going by the pattern.
Well, yeah, okay. Yeah, that's, well, yeah. I mean, if we turned it around the other way, I mean, okay. So they point out that this isn't so tricky after all. And then right next to this, let's draw the energy level diagram for the sodium atom. So here is the ground state, and this is called the ionization limit. So the ionization limit is something like 5.2 electron volts above the ground state. And, well, the ground state is a 3s state. For the alkalis, we can actually use hydrogenic labeling. And you have one outer electron not going around a nucleus, but you have one electron going around you have one electron not going around a proton, as in the case of hydrogen, but going around a core that has, you have one electron going around a core that has a charge of +1 because all the other electrons shield the rest of it. So the first excited state is the 3p state, and this is the D line. D line in the sense that Fraunhofer discovered this in the spectrum of the sun. So what color is the D line?
Yellow.
Yeah. So I was going to say, okay, good. And how do we know that?
Sodium lamps.
Because sodium lamps are yellow. Yeah. Okay. Yeah. So mercury lamps are like almost UV, and sodium lamps are yellow. So this is at 5890, 589 nanometers. Let's use the modern notation. Let's erase that, just to keep the diagram cleaner. So you have a 3p state here, 4s, 5s, 6s, and then they get all bunched together up here. You have a 3p and a 4p and over here, you have some 3D. This is in the book, so you don't, except in the crudest fashion, you don't need to draw this. But now you can see that if level B corresponds to an S state, which sort of does the way I drew the picture here, you'll get a resonance in the nonlinear susceptibility because of that. If level C or level A corresponds to a P state, well, you see this is almost corresponding to this, the way I drew the picture. So Miles and Harris implemented this. They looked up the known spectrum of sodium. They looked up the tabulated dipole matrix elements of all of these transitions. Now, people don't quote matrix elements usually, they quote oscillator strengths. But we'll get to that. The oscillator strength is a dimensionless number that tells you how big the dipole transition moment is. But they implemented this, and if there are enough, and they get a chart that looks like this. And I'll just schematically draw it here. They get chi3 as a function of the laser wavelength, and this is actually the log of chi3 on this axis, and they get curves that look like this. You can get destructive interference between two neighboring transitions. But the point is, you get a series of peaks in the third order susceptibility every time omega 1, every time omega, 2 omega, or 3 omega makes a resonance with an allowed 1 photon, 2 photon, or 3 photon transition of the sodium atom. I'll be charitable and say this was verified by experiment. Well, I mean, they didn't verify the entire spectrum of this. Motivated by this knowledge, they found a situation that they thought would give good conversion, and in fact, they got as much as a 10% conversion from neodymium 1.06 microns to 0.35 microns. They did that in rubidium vapor, and they achieved phase matching by adding xenon gas as a background gas. And that had a dispersion that was opposite to that of the sodium, because with xenon, you're below the resonance. With sodium, you tend to be above the resonances. So they even achieved phase matching. Okay, so this, okay. So now we can feel, now we can claim that the important parts of the chapter we've covered in lecture. My comment last week is that if you schedule a 3-hour class and you end 5 minutes early, you don't have to feel bad about yourself. But I will give you one more chance. Any questions? No, you're packing up your books. Okay, I'll see you next week.
We don't want you to feel bad about yourself.
Yeah.
Yeah, I didn't realize that.
Come by, come here.
don't fall asleep tonight and then wake up at 1 a.m. and be like, oh no, it's gonna be all over. I mean, I just flying